All right. So today we're going to finish up chapter 16 here and briefly talk about weak bases. And then we'll talk about the pH of salt solutions and periodic trends of acids. Let's see here. Then we'll start chapter 17 on Wednesday. Right. We should cover at least buffer solutions on that day, and then we'll see if we start talking at all about titrations and such, right? And then a week from today is your second exam, right? It's going to be on nuclear chemistry, equilibrium, acids and bases, and then whatever we get to on Wednesday, it's going to most likely just be buffer solutions, okay? Right, there will be a quiz on chapter 16 that will be due Wednesday. Right, that's already posted, though you won't be able to start it until tomorrow. And then sapling homework, right, is due Wednesday as well. Okay. Any questions about the class or the class material before we get going here? The group that has the exam on Wednesdays, the people that normally, like if you come into class, right, on Wednesdays, your exam will be Wednesday next week. If you come into class on Monday normally, your exam will be Monday next week, whether you're in person or online. Now, if you're online, right, you obviously don't come into class either of those days, but there's still that group of people who took exam on Wednesday online for the first exam. They'll still take the exam on Wednesday. People who took the exam on Monday online for the first exam will take the exam on Monday, right? So the day in which you take the exam does not change. Okay. You can see the list of people on Canvas as well. Okay. Any other questions? All right. So I guess we did start talking about weak bases. Now I'm kind of looking at about to right. A weak base is right just a base in solution that does not fully dissociate. Right. Strong acids, strong bases, 100% dissociation. Weak acids, weak bases, partial dissociation. Right. Typically, very small percentage of the weak acid or weak base dissociates in solution. So going back real quick to this question by Jordan here. No, so what I did between exams is last time the first exam date was on Wednesday, the second exam date was on Monday. This time, the first exam day is a Monday, the second exam date is a Wednesday, right? So the day you take the exam during the week does not change for the exams. I tried to make it so it wasn't that people who took exams on Wednesday always had to take it first time, and people who took it on Monday always had to take it the second time, if that makes sense, right? So the date in which you take the exam is unchanged. It's just that now the first day of the exam is a Monday instead of a Wednesday. That's what changed. Okay. Sorry about the confusion. All right. Right. So we talked about the base dissociation constant, the Kb, right? For some general base, right, reacting with water, forming the conjugate acid, and then the hydroxide ion, right, has a Kb expression of the conjugate acid times hydroxide ion concentrations divided by concentration of your weak base, right? Typical equilibrium constant expressions, right? Nothing new there. And then did this example last time of writing the Kb for ammonia and for acetate, right? Just show the screen just as a reminder, right? Last time we went over this, right? Wrote out those equilibrium reactions for the weak bases and then their corresponding Kbs, right? Which again is just the conjugate acid times OH minus over the weak base. Okay. All right. So right now, can ask questions like, what is the molarity of an aqueous ammonia solution that happens to have a pH of 11.17, given the Kb of ammonia is 1.8 times 10 minus 5. All right. So bringing up this problem, right? Again, in this problem, we're asking for what is the concentration, right? The molarity, that concentration of NH4 plus, right, equal to, in the solution that has a pH of 11.17, right? I'm sorry, not NH4 plus, that's ammonia. NH3, my apologies, NH3, right? That's the concentration we're looking for. What's the concentration of NH3? That's ammonia, right? Ammonium is NH4 plus. Sorry about that, right? Right, given the Kb is 1.8 times 10 minus 5, right? So again, right, this NH3 is a weak base. It reacts with water, right, to form ammonium, NH4 plus OH minus, right? And at Kb then has expression rate of equal to concentration of NH4 plus times concentration of OH minus all over the concentration of NH3, right? And that equals the 1.8 times 10 to the minus 5, right? That's given in the problem. Okay. Right. So again, I'm just kind of writing out what we know, right? What we're given, right? We're given that we have this ammonia in solution, right? We know ammonia in solution acts as a weak base and has this equilibrium reaction, which has a Kb of the following expression in the given numerical value, right? We're also told the pH is 11.17, right? And we're looking for, again, what is the concentration of ammonia here, right? Well, again, I have a problem that involves an equilibrium reaction, okay? And so it's going to most likely involve an ice table, right? So write out our ice table here, right? So this initial value of NH3, I'm just going to put concentration of NH3 here because we aren't actually given that, right? Water we don't care about. It's a liquid, doesn't matter, okay? Don't have any initial concentrations of our products, right? Have some change here, right, plus X on the product side, okay, X for the equilibrium concentration, right? And this will be concentration NH3 minus X, okay? Now, in the problem, we're told that our solution of NH3 produces a pH of 11.17, right? That pH of the solution is telling me, right, what the equilibrium concentration is of H plus, right? Because the pH, right, that equals negative log of the H plus concentration, right? And so, right, I can use that pH to get to what is the equilibrium concentration of OH minus, right? Because that's right here, X here, this equals the concentration of OH minus at equilibrium, which is related to the pH, right? And so I can calculate that concentration of OH minus. Again, there's a bunch of different ways, but one way we can do it is the pH plus the POH equals 14, right? So that gives me that the POH equals, what's the 14 minus that? 2.83, right? And so then the concentration of OH minus is then equal to 10 to the minus 2.83, okay? Right, that's how you convert from pH or POH concentration to H plus OH minus, right? You just take 10 to the minus pH or 10 to the minus POH, right? And so that equilibrium concentration of OH minus, right? This is our equilibrium concentration is equal to, I don't know if anyone has that number. It is 0.00148 molar. Okay. Oh yeah. Thank you, Jason. Right. So that is the equilibrium concentration of OH minus, right? And so that tells me what my change is. Okay. Right. But again, that then tells me what the equilibrium concentration of NH4 plus is, OH minus, but doesn't tell me the equilibrium concentration of NH3. Okay. Well, we're going to use the fact that this is a weak base that has a very small equilibrium constant, right? 1.8 times 10 to the minus 5, right? That this change itself is a fairly small number. Okay. And so we're going to use the approximation that we've used last time, in which, right, and again, this is a very common approximation to make for these weak acid, weak base equilibrium, and saying here that this concentration of NH3 minus X, this is basically just equal to concentration of NH3. Okay, right, that change when we round to our significant digits and such is going to be small enough that we're just basically whatever the initial concentration of our solution was. And so finally now I can plug this, and then given the fact that X is 0.00148 in to my expression up here for KB. So I have my KB, which is 1.8 times 10 to the minus 5 equals concentration of NH4 plus, which is 0.00148 times the concentration of OH minus, which is also 0.00148, divided by concentration of NH3. Okay. And then I can just multiply NH3 over the left side, divide by 1.8 times 10 to the minus 5. You'll get that the concentration of NH3 equals 0.122 molar. Okay. And so a ammonia solution of 0.122 molar has a pH of 11.17. Okay. Now you could, if you wanted to, right, use X here is 0.00148. Put that in the denominator here, and then solve for NH3. Okay. But again, if you do that and then round to say 3 significant figures, you'll get the same number. Okay. So you don't have to make this approximation, but it makes doing the math a lot simpler. Okay. And so it's often a very common approximation we'll use specifically for these, say, weak acid, weak base equilibrium, right? We never made this approximation at all when we did equilibrium problems in chapter 15. Okay, and that's because often the equilibrium we were dealing with in chapter 15 didn't necessarily have such small equilibrium constants. Okay, but when we're dealing with weak acids and weak bases, those equilibrium constants are typically very small, and so this is often a very good approximation. Okay, and the size of your equilibrium constant is much, much smaller than, say, the concentrations that you're dealing with, right? You're going to be fine making this approximation that the change is insignificant compared to the initial concentration of your reactant. Right. So questions about this example? All right. Okay. So kind of the next example, the data in the handout isn't necessarily given, but I'm going to post, on the slide here, right? You have a bunch of weak acids listed with their Kas listed, okay? And the question is, right, and also their conjugate bases are given as well. And the question is, out of the list of these 3 conjugate bases, or bases themselves, right? NO2 minus, PO4 3 minus, or N3 minus. Oh crap! Forgot I didn't give all of those. Let's change the question slightly here. Since not all those are given, let's instead do. Why can I never see the cursor on here? So Cn minus and ClO2 minus. There we go. So those are all listed in that chart. So we'll change up the problem here briefly. NO2 minus, ClO2 minus, or Cn minus. Which of these is going to be the strongest base? Anyone have a thought about this? Guess? So we get ClO2 and Cn minus, right? Right. So those are kind of the 2 extremes. If you want to write this table here, lists these acids from the largest Ka to the smallest Ka, right? So ClO minus is the largest on this table. Cn minus is one of the smallest, right? Right, which again, right, the size of the Ka tells us for the acid, like HClO2, right, that acid is a relatively strong, weak acid fuel, right? I mean, still considered a weak acid, but it's a much stronger acid than, say, HCN, right? HCN has a Ka of 4.9 times 10 to the minus 10. So it's very small compared to HClO2, which is 1.0 times 10 to the minus 2, right? So HClO2 is a much, much stronger acid than HCN, okay? But if HCl2 is a stronger acid than HCN, what that means for the conjugate bases is that the conjugate base ClO2 minus is significantly weaker than the conjugate base Cn minus, okay? So on this table here, right, and of the 3 given choices, right, the strongest base is going to be Cn minus here, okay? Right, and that's just because, right, for these conjugate acid-base pairs, the stronger the acid, the weaker the base, right? Because again, think of, right, for HCN, right? HCN is a very weak acid itself, right? Its acid dissociation constant is extremely small, right? Which means it really doesn't want to give up that proton. So let's say somehow you got that proton off of there and you're just left with Cn minus, okay? Well, if HCN didn't want to give up the proton, that's going to mean Cn minus really would like a proton back, right? Which is going to make it a stronger base, right? Because it's going to want to accept the proton. It's going to even want to almost take it away from something else, right? If it's a strong enough base, right? And so Cn minus acts as a much stronger base than ClO2 minus, okay? And again, we can know that because we know that HClO2 is a much stronger acid than HCN, okay? Right. Right, and I have, no, all right. Right, and how we know that, let me find a blank page here real quick. That will work. Right. And one kind of equation that was given on the lecture videos online on chapter 16, right, talks about the relationship between a weak acid and its conjugate base, and that the acid dissociation constant Ka for a weak acid times the base dissociation constant Kb for its conjugate base is equal to Kw, right? Kw being that equilibrium constant for water, right, which is 1.0 times 10 to the minus 14, okay? Right? And again, this is for conjugate acid base pairs, right? So this is only for conjugate acid base pairs, right? If I'm talking about hydrochloric acid and acetate ions, right, that are, one's an acid, one's a base, but they're not conjugate acid base pairs, this relationship does not hold up, right? This does not work. This is not true. This relationship between the acid dissociation constant and base dissociation constant is only true for conjugate acid base pairs, okay? Which tells me, again, right, it shows me kind of mathematically, right, that if Ka is very large, right, that means I have a strong acid. Kb has to be very small, and I have to have a very weak conjugate base, right? So again, for example, if we had a weak acid of hydrofluoric acid, or no, hydrofluoride, right? It's Ka, right? Again, as a reminder, is H plus F minus, or HF, right? And the conjugate base here is F minus, right? HF is our acid, its conjugate base is F minus. Kb, then for that, it's going to be concentration of HF, concentration of OH minus over concentration of F minus. Okay, right? And if you take the product of these things, simplify, you'll see that that equals Kw, concentration of OH times concentration of, concentration of OH minus times concentration of H plus, which is 1.0 times 10 to the minus 14. Okay. And so I can use this relationship here to convert. Say if I'm only given Kas, I can use this relationship to calculate the Kb of my conjugate base, right? By just taking Kw divided by Ka, right? And again, this mathematical relationship also kind of shows mathematically why the stronger your acid is, the weaker its conjugate base, right? We've talked about kind of why that is just in general in terms of when a molecule does or doesn't want a proton, right? But mathematically, right, we can also kind of see where that comes from in fact that if Ka is very large, Kb has to be very small. Because the product of those two things always has to equal 1.0 times 10 to the minus 14. Okay. Questions about this relationship? Okay. Again, this only holds true for conjugate acid-base pairs, right? If I were talking about HF and CN minus, right, this relationship is not true at all, right, because they're not conjugate acid-base pairs. And right, if you're wondering, are two molecules conjugate acid-base pairs? Well, if they only differ by, say, an H plus, then they're going to be conjugate acid-base pairs, right? Because your acid loses a proton to form the base, right? The base gains a proton to form the acid. Okay? Right? You notice all in this chart here, right? The conjugate base is just the same thing as the acid, right? Just minus an H plus. Okay? All right. So any questions about weak bases before we talk about salt solutions? Okay. Right. So what is a salt, right? Salt solution. Now, often, we'll talk more about this in chapter 17, right? But salts can often be formed by reacting an acid with a base to produce salt and typically water, okay? But a salt, right, itself is just an ionic compound, okay? So when we talk about salt solutions, we aren't necessarily just talking about like table salt, sodium chloride, right? But any type of ionic compound is considered a salt, okay? Right? Right, and so so some examples, right? Again, there's like that sodium chloride, calcium carbonate, potassium phosphate, right? Any ionic compound you can think of, right, is a salt, right? And those salts in water, okay, can affect the pH of a solution, okay? And how does that happen? Well, right, if I have a salt that contains, say, sodium acetate, right? Right, so if I have a salt with sodium acetate, right, that salt will fully dissociate in solution to create sodium ions and acetate ions in solution. Right? Let's just go over examples of these things, right? Right, so my salt is sodium acetate, CH3COO, right? That's my salt. I put this guy in solution, it's going to break apart. The sodium ions plus acetate ions, right? Well, sodium itself is just a spectator ion, right? You could think of it as sort of the conjugate acid, if you will, of the strong base, right? NaOH, okay? But NaOH is a very strong base. So this does not act as an acid, doesn't do anything in solution, right? Will not impact the solution. But CH3COO minus, right, is the conjugate base of a weak acid, and it itself is a weak base, okay? So I put this in solution, sodium is going to do nothing, okay? But CH3COO minus will react with water, right? And that Kb reaction forms CH3COOH plus OH minus, right? Which this reaction produces hydroxide in solution, which impacts the pH of that solution, right? Because if I increase the hydroxide ion concentration in my solution, that means I must be decreasing the hydrogen ion, right, concentration in my solution, right, which will increase the pH of this solution, right? So solution of sodium acetate will have a pH greater than 7, right? Because I've introduced a weak base into the solution, so that base, right, is going to increase the pH. Okay? right? But if I had, say, potassium chloride, I add that to solution, right? That's going to break apart into potassium ions plus chloride ions, right? Right, chloride comes, right, is sort of the conjugate base, if you will, from hydrochloric acid, right, which is a strong acid. So this chloride ion does not act as a base, and the potassium ion is not going to be acting as an acid in solution, right? So neither one of these ions are going to do anything in solution. So this solution will just have a pH equal to 7, right? The pH is going to be unchanged because these ions are not going to react with water in any way to form hydrogen or hydroxide ions, so it's not going to impact the pH at all. Okay. All right. And so when figuring out how a salt, right, can impact the pH, we got to see, right, does that salt come from some sort of weak acid or weak base, right? So that it itself is a weak base or a weak acid, like acetate or ammonium, right? Or does it come from some sort of strong acid, strong bases, right? Like the examples of these ions down here, right? Where all of these ions, all these anions, right, are not going to act as some sort of base, right? Now, HSO4 minus is the only exception here, right? HSO4 minus itself is a weak acid, so make a solution more acidic, okay? You put HSO4 minus in solution, okay? Right? And then things like sodium, lithium, calcium, barium ions, right? Those cations, right, are not going to impact the pH of your solution. They come from strong bases, so they themselves don't do anything. They'll just be spectator. Okay? Right. So these are kind of your list of common kind of spectator ions, right? I mean, there's like potassium and, right, other of these group 1, group 2 cations, right, are very common. Yeah. So let's consider these examples as whether or not they're acidic, basic, or neutral solutions, right? So first, let's consider sodium chloride, right? From sodium ions, chloride ions, is that solution going to be acidic, basic, or neutral? It's going to be a neutral solution, right? Because the sodium and the chloride ions, right, come from strong acids and strong bases, so they themselves do not interact with water or anything else. These are just going to be spectator ions in solution, right, just floating around doing nothing. Okay. Right. So that will have a neutral pH, right? Sodium acetate, okay? C2H3O2 is another way of writing that acetate formula, CH3COO minus, okay? The sodium acetate in solution, is this solution going to be acidic, basic, or neutral? People saying acidic. Right, so again, we've established, right, sodium doesn't do anything in solution, but the acetate ion here itself is a weak base. That weak base will react with water, right, to undergo that equilibrium reaction. Okay. Undergo this equilibrium reaction, right, with water to produce hydroxide ions in solution and the conjugate acid. And so its pH is going to be greater than 7, so this is going to be a basic solution. Right? So here, the sodium acetate is going to form a basic solution because effectively, right, you've introduced a weak base into solution, right? So you add a base to a solution, the solution is going to become a basic solution, right? So here, I have ammonium bromide that produces NH4 plus ions in solution and Br minus ions in solution. Okay. The solution would be acidic, basic, or neutral. NaCl was a neutral solution, Jordan. Okay. It was neutral. Okay. And so for this solution, it's going to be acidic, basic, or neutral. It's going to be acidic, right? NH4 plus is a weak acid. It will dissociate to NH3 plus H plus ions in solution, which will lower your pH and make it an acidic solution, right? So you've introduced a weak acid, NH4 plus in the solution, right? Well, Br minus itself is, again, a spectator ion that comes from a strong acid. It will do nothing in solution, right? So you can ignore the Br minus. You just have this NH4 plus in solution that establishes an equilibrium that will lower the pH of your solution, making it acidic. And then this one, NH4 plus plus Cl minus. This is sort of actually a trick question. We need more information. We don't know. Okay. In this solution, NH4 plus, as we just talked about, right, is a weak acid. So it will undergo that acid dissociation equilibrium reaction, right? That will lower the pH. But Cn minus, as we talked about, is a weak base. So that will react with water to produce hydroxide ions in solution, which will want to raise the pH, right? And so the actual pH of the solution will depend on how strong of an acid NH4 plus is versus how strong of a base Cn minus is. Okay, so you need more information to be able to try to figure out whether or not this solution is acidic, basic, or neutral. Okay, so this is kind of a little bit of a trick question in which we don't know. Okay. Now, given, I think, KAs, if I recall from the chart earlier, I believe this will end up being basic because I think Cn minus is a much stronger base than NH4 plus is an acid. But again, that's my speculation. I haven't really worked it out to know for sure. But yeah. So just kind of summarize this, right, of these examples, right? If your salt, right, if the ions from your salt come from both a strong acid and a strong base, then your salt is going to produce a neutral solution, right? pH equal to 7, right? If your salt, the anions and cations, right, come from strong acids and weak bases, okay, then you've added some sort of weak acid to that solution, which is going to form hydronium ions, right? It's going to make it acidic, okay? If your salt comes from a strong base and a weak acid, that means the salt is introducing some sort of weak base in solution, and that weak base will react with water to form hydroxide to make it a basic solution. And then right, if it comes from both weak acids and weak bases, then it could go either way. We don't know, right? You need more information to kind of determine that. Okay? Question here. So if it comes from a weak acid or base, the pH changes. Yeah, right. If you're introducing a salt in solution where the anions or cations of that salt came from weak acids, weak bases, which makes them a weak acid, weak base themselves, the pH of that solution will change. Okay, for sure, pH will change. Now, we can tell whether or not it's going to increase or decrease if only one of those ions is a weak acid or a weak base. But if both of these equilibrium are occurring, right, the BH plus equilibria and the A minus equilibria, both of those are occurring in solution, which is what's going on in the bottom right box, then we don't exactly know how the pH will change because we need to know which of these things is a stronger acid versus stronger base. So we kind of need more information to be able to calculate that, which we won't do in this class, but in general, you would need more information to calculate it. All right. So some more kind of questions related to this, right? Which of the following compounds will produce a basic solution when dissolved in water? Sodium nitrate, hydrofluoric acid, NH4Cl, Na2CO3, or NaCl. Anyone have any thoughts? Which one of these salts or compounds will produce a basic solution? People saying A or D here. Anyone else? Right, so these are options, right? A, B, C, D, E, right? So NaNO3, right? This is Na plus NO3 minus in solution. Will Na plus impact the pH? No, right? Na plus comes from NaOH, right, which is a strong base, so it does not change the pH, right? NO3 minus, will that impact the pH? No as well, right? Because NO3 minus comes from HNO3, the strong acid. So NO3 minus is also not going to impact the pH, okay? HF here, so this will have a pH equal to 7, right? This will be a neutral solution, right? Okay, because neither sodium or nitrate ions will impact the pH, okay? Right? Then HF here, what is HF? A what now? Close, it's a weak acid, okay? So it will undergo this equilibrium reaction in solution, right? Which will introduce hydrogen ions, right? Which will have a pH less than 7, right? This will be an acidic solution, right? Because I've added a weak acid in solution, right? HF is a weak acid, and so it will lower the pH of the solution, making it acidic, okay? NH4Cl is a salt, right? It breaks apart in NH4 plus ions plus Cl minus ions, okay? NH4 plus, will that affect the pH? Yes, right? NH4 plus is a weak acid. It will make the pH less than 7. This will be an acidic solution. The Cl minus will not impact the pH, okay? Cl minus is a spectator ion, right? This will be acidic, right? pH less than 7, right? Na2CO3 here forms 2Na plus CO3 2 minus, right? Na plus, right? Is that going to impact the pH? No, right? Again, it comes from a strong base. Okay, so that will not impact the pH. CO3 2 minus. Yeah, CO3 2 minus is a weak base. Okay, CO3 2 minus will react with water, form HCO3 minus plus OH minus, right? Which lowers the pH because, or sorry, raises the pH because it introduces hydroxide ions, right? So this is a basic solution. So D here is the answer, right? And then sodium chloride, right? Na plus Cl minus, right? This will have a pH equal to 7. This is again, sodium and chloride come from strong acids and strong bases, so they will not change the pH, right? And again, how did I know that ion, CO3 2 minus, was a weak base? Okay, I know it's a weak base because its conjugate acid, HCO3 minus, is not on my list of strong acids. Okay, right? So if you're kind of wondering as we're doing this problem, how did I know which things were not in fact impacting the pH? I know those by knowing my list of strong acids and strong bases. So if you have not already kind of gotten that list of what is a strong acid, what is a strong base down in your head, I very much recommend that you remember those lists of strong acids and strong bases, because that's basically all these problems are, of identifying whether the pH of a salt solution is acidic, basic, or neutral, right? Is knowing, okay, these cations, these anions come from strong acids and strong bases, so they don't impact the pH. Well, this anion, CO3 minus, is not from a strong acid or strong base, so it itself, right, and it doesn't have any protons to donate, So it's going to be a weak base, right? Reacting with water to form HCO3 minus and OH minus, right? Right, NH4 plus, right, comes from a weak base, NH3, okay? And that itself is an acid, right? It can donate protons to solution, right? And so that will change the pH, okay? But again, a lot of this is identifying what are your strong acids, strong bases, weak acids, weak bases, so that you know which of these ions actually affect the pH of a solution, okay? Right? Questions about this example here, this question?
So you concluded that CO3 2 minus was a weak base because it came from HCO3 minus.
Yeah, but basically because, right, it's conjugate acid, right? If I want to think of, right, I mean, I know it can't be an acid because it's got no protons, right? An acid, right, has got to donate some protons. So if it has no CO3 2 minus has no protons, so it can't be an acid. So, and it itself is then going to be a base with its conjugate acid being just that molecule plus a hydrogen ion, right? Which is not in my list of strong acids, right? If we were to go back at the beginning of the slides here, right? The list of strong acids does not include HCO3 minus, right? Includes like HCl, HI, HBr, HClO4, NO3, H2SO4. I might be forgetting one, right? But and so yeah, so I knew this had to be a weak base. Because it can't necessarily be a weak acid, right? And basically these ions in solution, right, can either act as an acid or a base because they can either react with water to donate a proton to water or to take a proton away, right? Any ion in solution, right, can technically, now whether or not they're strong enough to act as an acid or a base is a different question, but we're not asking that question, right? We're just asking whether or not things will act as a base or not, right? Any anion, A minus, say, could react with water, right? To say form like HA plus OH minus, right? Typically any cation, called B plus, right? Could also react with water to form, right? Right, these ions can react with water to either pull a hydrogen away from water to form OH minus, right? Or could somehow have, well, no, it can't. Yeah, if it doesn't have a hydrogen to donate, it just can't act as an acid, right? So basically, they're typically going to act as a weak base. There's very few ions like NH4 plus here that can actually act as an acid, okay? So most of the ions that you're introducing in solution are going to act as bases, okay? Let's see, go back to the slides here. Right, basically these kind of ammonia-like molecules, I think here, I have another example, no. I don't have another example on the slide here, but for the, there's very few cations that donate protons and anions that donate protons, right? Your list of things that can be, that are an ion and can be a weak acid are like NH4 plus, and then your polyprotic acids, right? Or after they've donated like a proton, HSO4 minus, right? H2PO4 minus, right? These polyprotic acids, right? They're ion forms, right? So if I write some of these down, right? All right, H2PO4 minus, right? This could act as an acid because it's got a proton to donate, right? CO3 minus, right? This itself can act as a weak acid, right? These polyprotic acids, right? And then like NH4 plus are, for the most part, the only types of compounds that are ions that also can act as weak acids, because they have to have a proton to donate to act as a weak acid, right? And so most of the time, these ions are going to be weak bases when they react with water. But again, it's not 100%, but most cases. But again, I knew this had to impact the pH, whether it made it more acidic or basic. I knew CO3 had to impact the pH because, right, adding or removing a proton from that does not form a strong acid or strong base, right, for this guy. Okay. That was kind of a long answer to your question. I hope that actually answered the question. All right. Other questions? Yep.
Can you explain what is seen as thick pigment?
Cl minus comes from its conjugate acid is a strong acid, HCl. And so Cl minus itself doesn't impact the pH at all. Basically, go back to this slide. Right? So ignore HSO4 minus here. But I guess I can write out some stuff, right? So if I were to, oh, shoot. I can't, there it is. There's the cursor, right? So let's ignore this real quick, right? Okay, plus, what are some of the, plus, right? Trying to think, right? I mean, I could write out your group. These are, your list of cations and ions that don't impact the pH, right? Those group 1, group 2 ions, essentially the cations, right? And then your anions, Cl minus, Br minus, I minus, NO, right? Those are it. Those anions, any anion that aren't these is going to impact the pH in some way, basically. The cations, right, that aren't these kind of group 1, group 2s, could impact the pH, right? Because all the rest of these will come potentially are conjugate acids or conjugate bases of weak acids and weak bases in solution. And so here, NH4 plus is a weak acid itself, so it will lower the pH, and then Cl minus doesn't change the pH at all, so that is why that solution ends up being acidic. Other questions? All right, okay, we just did this, right? It's an acidic solution when you dissolve NH4Cl in water. Okay. Right, and this is another way of kind of asking the same type of question, right? I've introduced sodium acetate in the solution. What is the reaction responsible for the pH change in that solution? Is it A, B, or C? Yeah, it's going to be C here, right? A is just the dissociation of that ion into ions, which doesn't change the pH itself, right? But then once acetate reacts with water and forms acetic acid and OH minus, that will change the pH, right? And then this reaction B here just doesn't happen, right? This reaction B will never happen in solution. Sodium's never going to react with water, form sodium hydroxide and H plus ions, okay? So this never happens. But C here can happen and does happen, and that will impact the pH. Yep. All right. Which of these things will have the solution with the pH closest to 7? Okay. So let's kind of talk about this together. For sake of time, make sure we cover our periodic trends, which are going to be next, right? So KNO3, right? This forms potassium ions and nitrate ions in solution, right? Do potassium ions impact the pH? Nope. Nitrate ions? Nope. Right, so A here, all right, okay, this is going to have a pH of 7, so it's probably going to be the closest, right? CO2 is kind of a trickier one. CO2 will actually react with water to form carbonic acid. So this is part of the reason why soda is acidic. CO2 plus H2O will form H2CO3. Oh, that H2CO3 kind of carb C and O kind of blended together. So, right. So water, CO2 will actually, when dissolved in water, will react with it to form H2CO3. Okay. Sort of an equilibrium reaction. It's not a very strong equilibrium reaction, but it will produce this weak acid, which will change the pH of your solution. So, right, if your soda had nothing else that impacted the pH but just the carbon dioxide, which gives it, the bubble, right, the, fizziness to it, right, then it would be acidic. Okay? So B is actually an acidic solution. C here, I have NH4 plus on, and then iodine in solution. Okay. Does NH4 plus impact the pH? Yes. Iodine, I minus. Nope. Right. NH4 plus is a weak acid, so it will lower the pH. So C will also be an acidic solution. NH3. What is NH3? A weak base. Yep. And so that will raise the pH. Okay. And then NH2CH3 is also a weak base. Okay. This will react with water to form NH3CH3 plus hydroxide ions. Okay. So this E here is a weak base as well. And this will be a basic solution, just like D. Okay. So A here is the only one that's going to be a more neutral solution. B and C are acidic. D and E are basic. Okay. Question? We'll come back to this calculation here in a second. I want to make sure just talking about kind of went over those. Talk about the effect of structure, okay? And then again, given time, we'll get back to that last kind of example, workout in person, okay? So things that can affect the strength of an acid, okay, right, can be things like the bond polarity, okay, right. The more polar a bond is, typically is related to the weakness of the bond, right. So bond polarity here referring to things like an HCl bond versus H-iodine bond. The bond polarity, right? So if I have like ClH, right, this is a polar bond, right, where the electrons from the hydrogen are kind of being drawn into the chlorine. This is the difference in electronegativities, right? And then, HI, right, iodine, hydrogen, right, similar type of polar bond and things like that, right? So bond polarity, as well as the strength of the bond, right, can impact the pH, right? Because, right, if we consider an acid, right, an acid is something that donates a proton, right? To donate a proton, I got to break the bond here, right, that exists in these molecules, right? So if I got to break that bond, it's a lot easier to break the bond if it's a weak bond, right? And so if the weaker your bond is, the stronger your acid is going to be, because the easier it is to break that hydrogen bond in your molecule to donate the proton, okay? And that's related with the stability of the conjugate base, okay? And these type of effects of structure have the following kind of periodic trends for binary acids, okay? So for binary acids, right? Binary acids meaning like HCl, HI, right? H2S. Okay, so acids that just have hydrogen and some other atom, right? Those acids, the acidity, right? The strength of the acid increases, right? From left to right. So as you go to the right of the periodic table, you get to a stronger acid. Okay, and then as you go up and down the periodic table, it increases with increasing atomic number, or increases as you go down the periodic table, right? So I have a picture of the periodic table here, right? But again, as you go to the right and down a periodic table, these binary acids, which again, it's just hydrogen with some other element, right? HF, HCl, HBr, HI, H2S, HO, right? H3N, right? All these things, right? These are binary acids, right? And the strength of the acid increases as you go to the right and down the periodic table, right? Which is why your strongest acids for these binary acids are Cl minus, or sorry, HCl, HBr, and HR, right? Those are the things on the furthest right and down on the periodic table, right? Or the halogens, okay? Yeah, so that's why HCl, HI, and HBr end up being strongest acids, okay? But HI, for example, is a stronger acid than HBr, because again, it's further down the periodic table, okay? And that's just because as you get to these with these binary acids, as you go to the right and down, the bond strength between the hydrogen and that atom gets weaker and weaker and weaker. Okay, so the strength of the bond between HI versus HCl, right, is much weaker for HI than it is for HCl. Okay, and then for oxy acids, kind of have two different potential changes, right? So an oxy acid is H2CO3. H2CO4, right? H2SO4, H2SO3, right? These oxy acids, right, are again some sort of element oxygen compound that is an anion that then has some hydrogen thrown on. Okay, HClO3, HClO4, right? All those types of acids, right? I have some. Right, these are examples of oxy acids, right? H2SCO3, right? These are oxy acids, okay? So again, they're called oxy acids because they got, a bunch of oxygens in the acid, okay? So for these oxy acids, right, if you have the same structure, meaning the same number of oxygens, okay? So I could have said, instead of same structure, I could say the same number of oxygens. The acidic strength increases with increasing electronegativity on that central atom, okay? We'll see an example of that in a second, right? And then if the central atom is the same between my oxy acids, the larger the number of oxygens, the stronger the acid is going to be. Okay. So let's do that example first, right? So let's look at this example where I have 4 different oxy acids here. I know which is the strongest and which is the weakest, right? So when I compare these oxy acids, let's compare, say, A and B here, right? For A and B, I have the same number of oxygens, okay? So what matters is the electronegativity of sulfur versus selenium, okay? Which electronegativity increases as you go up the periodic table and to the right. If you remember those periodic trends from Chem 1, right? Up and to the right for electronegativity. So sulfur is above selenium on the periodic table. So sulfur is more electronegative, okay? So if I'm comparing A and B here, B is going to be the stronger acid and A will be the weaker acid of those two, right? Because again, S is more electronegative, so it is a stronger acid, okay? And that's the same thing if I compare C and D, right? C and D have the same number of oxygens, and so it's just the difference between sulfur and selenium. And so H2SO4 is a stronger acid than H2SeO4, okay? Now, if I compare, say, B and C together, right, there I have the same central atom, sulfur, right? That sulfur is the central atom. And so I have different number of oxygens, and the compound with more oxygens is going to be the stronger acid. So H2SO4 is the stronger acid out of H2SO4 and H2SO3. So if we were to list these from acidic strength, right, and let's just, I guess, finish it up, right? Compare A and D here, right? H2SeO4 is going to be a stronger acid than H2SeO3, okay? So if I had to list these in terms of acidic strength here, H2SO4 is the strongest acid. Then I'd have H2SO3, then H2SeO4, and H2SeO3. Okay? Right, so the weakest acid here is going to be this A here, H2SeO3, because the central atom is has the weaker electronegativity, and the number of oxygens is the fewest, right, the smallest. Okay? The fewer oxygens and the more weaker electronegativity on the central atom produces the weakest acid. Okay, so A here is the weakest acid of this group. Yeah.
Okay, so if they were asking to list them, would you put electronegativity for
Number of oxygens? Yeah, as I was doing that, I was realizing there's not a great way to know for sure. So I kind of stuck with it. But yeah, I mean, right, so the question is, right, when you're listing these things, when you're comparing, let me just write out SeO4 versus H. Right. So if we're right, the main question is the relative strength of these two acids, right? Because we know H2SO4 is a stronger acid than H2SO3, and we know H2SeO3 is a weaker acid than H2SeO4, right? But the question is this the right order in terms of most acidic, least acidic, or do I flip these two things around? And actually, it's going to actually kind of depend. And so you wouldn't really be asked a question like this where you have to list them in order because it's not too difficult to tell. So the actual order of these two things could be swapped. And it really just depends on whether or not, how big is that electronegativity difference between your central atoms? How many oxygen differences do you have? So it's very, very specific. And it's not straightforward and easy to tell by just looking at it. So yeah, so I can't necessarily tell which one of these is stronger than the other, right? But I can tell at least this is the strongest and this has got to be the weakest, right? So that I could at least ask, what is the strongest or what is the weakest acid out of this list, right? Okay, but I wouldn't necessarily be able to answer the question, list these in terms of acidic strength. All right. So which of the following binary acids is the weakest, right? So if we look at these right, they're listed in terms of their order in the periodic table. This is the furthest up in the periodic table. This is the furthest down. For these binary acids, right, the acidic strength increases as you go down the periodic table. So A here, HF, is the weakest acid. Okay. Right, and the last kind of topic to talk about here for chapter 16 is Lewis acids and Lewis bases, right? This right is just a kind of reminder. We talked at the beginning of the chapter 16, right? A Lewis acid is an electron pair acceptor, right? And a Lewis base is electron pair donor, right? And that definition allows you to include reactions like this here, where NH3, right, donates its electron pair to BF3 here, form this compound, okay, right? And while this is not an acid-base reaction in terms of the Bronsted-Lowry definition, okay, there's no protons being transferred, this NH3 still acts as a base in terms of the Lewis definition, right? And then BF3 here can act as an acid according to the Lewis definition. So this would still be considered an acid-base reaction, right? According to the Lewis definitions of acids and bases, right? And all the other acid-base reactions that we talked about for Bronsted-Lowry definitions still be acid-base reactions according to the Lewis definition of an acid and a base, okay? So again, this Lewis definition just expands upon what types of reactions can involve acid-base reactions and why this Lewis definition is important, okay? So again, right, this typical acid-base reaction that we think of, right? Again, you have the same thing as the acid. This HCl is electron pair acceptor, right? Because the chlorine accepts the pairs of electrons, right, to form Cl minus. And then NH3 is donating its proton when it forms NH4 plus, okay? Or sorry, donating its electrons, not the proton, right? It's electron pair, okay? So it's still an acid-base reaction in the Lewis definition, okay? But you have these other reactions like the formation of these coordination complexes, okay? Right, where a coordination complex is some structure here where you have some central metal ion, okay? And then a bunch of molecules, often called ligands, where you have 4 to 6 of these molecules that surround that central ion. So here, example is iron H2O6, okay? Right, this is a coordination complex, and the formation of this complex is a Lewis acid-base reaction where the ion acts as a Lewis acid, and these ligands act as Lewis bases, donating their electron pairs to the central metal ion. Okay. And then here's some just examples of different ligands, right? So water could be a ligand here where it has an electron pair to donate to these metals. Ammonia, chloride, cyanide, right? These different ions here can all act as Lewis bases, right? Where they donate an electron pair to some metal ion in solution, like say this iron ion, okay? And so, right, this is why kind of the definitions of Lewis and acid bases are relevant and important, okay? It's because it then allows us to discuss kind of chemistry beyond, say, proton transfers in terms of acid-base chemistry, okay? So going back real quick to some of these examples, right? So let's go to first some of these salt questions, right? So if I have sodium carbonate, dissolve it in water, will the solution be acidic, basic, neutral, or will I need more information? It's going to be basic, right? Sodium ions will do nothing in solution. CO3 minus acts as a weak base in solution to form HCO3 minus. And so again, CO3 minus is a weak base, so it will form a basic solution when added solution, right? And then here, NaHCO3. So it'll be acidic, right? HCO3 is a weak acid, right? It forms that CO3 2 minus weak base, right? It's conjugate base, but HCO3 minus is a weak acid, so it will form an acidic solution, A here. Okay. Right, potassium chloride, be acidic, basic, or neutral, or more information. It's going to be neutral, right? Potassium and chloride both are expectorate ions, right? They come from strong acids, strong bases. This will be a neutral solution, okay? Right? So this was that example, last example that we didn't do a minute ago, right? Just kind of talk about how we solved this example last 5-6 minutes so last here, right? So in this example, right, I want to know what is the concentration of OH minus and the pH for a 0.1 molar solution of sodium cyanate, Cn minus here, right? Given the Ka for HCN is 4.9 times 10 to the minus 10. Okay. Right. So again, I have, right, the salt, or now I'm specifically looking, right, if I add this salt to solution, right, NaCN forms Na plus Cn minus, right? The sodium ion does nothing in solution, right? It will not impact the pH, right? But Cn minus is a weak base, right? And I'll have Cn minus will react with water, form HCN plus OH minus, okay? And this will change the pH, right? So again, I have this weak acid, weak base equilibrium, okay? So it has, right, a Kb equal to the concentration of HCN times concentration of OH minus over concentration of Cn minus, okay? Now for this problem, we aren't given the numerical value of Kb, but we are given the value of Ka. So how do I get Kb from Ka? Yeah, like Kw equals Ka times Kb. For a conjugate acid-base pair, right? HCN, Cn minus are conjugate acid-base pairs. So I can calculate Kb by just taking Kw divided by Ka, right? So that Kb is equal to 1.0 times 10 to the minus 14 divided by 4.9 times 10 to the minus 10, right? That is the numerical value of Kb, okay? And so I have my equilibrium constant, I have the equilibrium constant expression, I have this equilibrium reaction, right? And I need to find out what are the equilibrium concentrations of OH minus, right? In order to get then the pH as well as that concentration of OH minus, right? And so to do that, we have to use an ice table, right? Start off with 0.1 molar of Cn minus. Water I don't care about. Start off with nothing of HCN and OH minus, okay? Right, and I know I have 0.1 molar of Cn minus, right? Because when this breaks apart, right, 0.1 molar of NaCN forms 0.1 molar Na plus and 0.1 molar Cn minus. So again, I lose some amount of my reactant, gain some amount of my products, okay? Again, this is going to be a weak base, okay? So I'm going to approximate the equilibrium concentration here is just basically 0.1, okay? This is an approximation, right? I'm just ignoring X here, right? This is an approximation, right? Just so, you know, we aren't confused as to why, what happened to minus X here. I'm saying 0.1 minus X is basically 0.1, right? And then this is X, this is X. So now I can plug in these equilibrium concentrations into my Kb expression here to get X times X divided by 0.1 equals whatever that number comes out to be. So I have that written down. Let's see here. That is equal to 2.04 times 10 to the minus 5. Okay. And so then I multiply 0.1 over, right, to get X squared equals 2.04 times 10 to the minus 6. Take the square root of both sides to solve for X, which is the concentration of OH minus, right, the square root of 2.04 times 10 to the minus 6. Okay. I don't have that number written down. More. Square root of that. Okay, so the concentration of OH minus equal to 0.00142 molar. Okay. There's a question here real quick. Where did the 10 to the minus 14 go? So this 1.0 times 10 to the minus 14 equals Kw. So that's where that came from. So that's concentration of OH minus, right? And then to get the pH, again, I can solve it however I want. I like to find the pOH and then do 14 minus the pOH equals the pH. Okay. So the negative log of that gives you a pH of 11.15. Okay. So, right, this sodium, sorry, NaCN solution, right, of 0.1 molar has a pH of 11.15, right? Okay. Given kind of information in this problem, right? So I know I kind of ran through that quickly. You know, I'm happy to answer any questions if people want to stick around to ask, right? Otherwise, you know, class period is now finished, so you're welcome to leave. But again, if you have questions about this example, I'm happy to go over it. Make sure to turn in your participation questions for the day at the back table as you're leaving. Okay. And if those here on Zoom have any questions, you're welcome to ask them as well. right, doesn't look like it, so I'm gonna close the Zoom session. See you guys on Wednesday.